Hello everyone, and welcome back to another Eng 130 video tutorial. As you guys recall, in the last tutorial we looked at what happens if one of the rollers in a support reaction is at an angle, and now we're going to take it kind of a step further into a problem that professors love, and I mean love. I'm almost willing to bet it'll be on the final, just because it's such a good problem, man, but it's really evil at the same time. And that is not when the roller is angled, but when the beam itself is angled. Think of our roof truss. That'd be the best kind of example. The beam goes up at an angle. So how do we deal with that? So this tutorial is hopefully help you show what we do when it's at an angle. And the thing is, it's actually the exact same procedure as what we'd regularly do. But the only difference is students see the angle and they start to overthink everything, and well, it gets actually quite entertaining for me anyways, because you guys come up with stuff I've never seen before. You guys prove some crazy trig stuff, but it's actually really simple, but it's such a good scare tactic. When people see things at an angle, it just freaks them right out, and that goes for everything. So let's just jump into the example, and hopefully you guys see what I mean, and hopefully I can ease your mind a bit when it comes to beams at angles. So let's begin. Alright, so the question itself, very, very simple. It wants us to determine the reactions at the supports. So very simple question, very straightforward question. This would probably be part A of, let's say, a truss question, because in order to start solving trusses, as you guys will see, one of the first things you guys are always going to have to do is determine those support reactions. So again, like everything else, and I can't stress this enough for the rest of the course, everything, best thing to do is going to be draw a free body diagram. So let's go to our marker, and real quickly, let's just draw our beam. So we kind of see that we have something like this. So let's make it just a little bit longer, and let's just say that. So next thing what we're going to have to do, well, let's put in some of our support conditions. So we see that we have kind of a roller right there at point A. So what I'm going to do is I'm going to call this AY, because this one's not angled like the previous one. It's actually going in a vertical direction, so it's nice and easy just to put AY. And we see for B, we have a pin. So there's going to be two connections. So one going vertical, one, oops, that kind of backfired. So let's just change it real quick. Why not? Because these are going to be the exact same. So this one's going to be BX and BY. So far, not that scary. So far, even though the beam's at an angle, the support conditions are still regular. It doesn't really change. But now it gets a little bit more crazy when we have this distributed load, because as we see, this distributed load acts at an angle. So what I like to do for distributed loads, as you guys know, is I'm just going to kind of put a dotted line going across to show the silhouette of the distributed load. So very, very tedious, but when you guys have your nice ruler or straight edge with you, it's very, very fast. So something kind of like this. And then what I like to do is I'm just going to put the distributed load where it acts somewhere in the middle. So I'm going to put a big arrow right here, and I'm going to call this distributed load F1. Actually, I guess I don't need the 1 because it's going to be our only distributed load. So we should also put the parameters of the distributed load, so we know it's 800 newtons per meter. So not a huge distributed load, but still something. And then the next thing that we should always do, of course, is dimension our diagrams. Remember, it's a very, very key part. So let's go right to the end of the beam, something like this. So we know that it's split up into two sections horizontally. It's kind of from B to A, and then from A to the end of the beam. And we know that the first part is 1 meter. The second part is going to be 3 meters. And the second part is going to just be the height of the beam, which that looks terrible. Something like this. Oops, I don't know why this isn't, that's kind of cutting off there. Let's go a little bit further back. Maybe I got a smudge there or something. So we can do something like this. And we know that this is going to also be 3 meters. So not exactly to scale, but again, it doesn't really matter as long as it's clear. So right now we have all of our unknowns, all of our dimensions. So it's not going to be too bad. So real quick, we can see that the bottom length is 4, and then the height, I guess the horizontal span of the beam is 4 meters, the vertical span is 3 meters. So we can actually tell really quickly that the actual length of the beam, so something like from here to here, is going to be 5 meters. So that's just the 4 squared plus 3 squared, all square root, as easy as it gets. And the reason why we're finding that real quick is because we want to convert that distributed load into a force. So we know that F is going to be 800 kilonewtons per meter. So that's kind of the magnitude. And then we know it runs a distance of 5 meters. So it's going to be times by 5. And what we get is 4,000 newtons. So now F is known. So it's perfect. And we know that F acts at a distance halfway across the beam. So we know that the distance from F to, let's say, B is just going to be 5 divided by 2. So it's going to be 2.5 meters. Alright, so now we kind of have everything that we need. Now we can start going in and solving for everything. So the question, again, very, very simple. Determine the reactions at the supports. So before we start looking at angles really quick, I want to show you guys something which is really, really, really nice. And that is if we sum the moments at the pin. Because remember, that's what we usually do. We sum the moments at the pin, see where it gets us, because it usually eliminates 2 out of 3 unknowns, 1 unknown left. Very, very nice. So let's just go down here and let's just go sum of the moments. And our pin right now is at B. So let's go sum of the moments at B is equal to 0. So we see that Bx and By will create no moment because they intercept that point. The distance would be 0. So that leaves us with F and Ay. So let's start off with Ay real quick. And we realize, okay, it's actually nice because we already have the distance. Ay is already vertical. It's not at an angle. So we know that it'll be Ay times its distance, which we know is going to be 3 meters. And if we look at the rotational tendency of Ay, so if I hold my pencil at B and I push up on the left side, we see that it starts to rotate clockwise. So we know this will be more of a negative. So then we got to go, okay, well, the next component is going to be F. And we know that F can be split into an Fx and an Fy because it's at an angle. But here's kind of the trick to this. Remember, when we're taking a moment, it's going to be the force times its perpendicular distance. And if we look at this 2.5 meters right here, we see that that's actually already its perpendicular distance. We don't have to convert F into X and Y. Of course we could, and we can find those new distances. We can definitely do that, but it's actually not needed in this case because it's just going to be F. So we know that F is going to be 4,000. And we already see that the perpendicular distance right here is 2.5 meters. That's the perpendicular distance, because remember, this distance measured on F, this is perpendicular right there. Perpendicular distance to B, we're good to go. So 2.5, and that's our last force, so we know that this is all going to be equal to 0. And real quick, we have to look at the rotational tendency of F. So if I hold my pencil at B and push down where F would be, we see it starts to rotate counterclockwise. So this is going to be positive, which is kind of expected. So if we do all the math, what we're going to get is Ay is going to be equal to 3,333 newtons. And the direction for that is upwards. So we already have one of the unknowns, and we didn't even have to solve for the beam being kind of diagonal. Or sorry, yeah, the beam being diagonal. Diagonal is probably not the best word. I'd say just angled, applied to more of a better situation. But now, our next step, of course, would be using our other equilibrium equations. So there's some of the forces in X, or some of the forces in Y. But the problem is F is now at an angle, and if we're finding the components of F, we're going to need to find out what kind of angle F is at. So this is where it gets kind of messy, if you will. So let's go down here, and I just want to draw something real quick. So hopefully this will help you guys figure out what's exactly going on with the trigonometry, because you guys are all pretty smart at trig. You guys can handle this just fine, but let's just take a quick look. So let's just say we have our beam, it's angled, and we're given this right here as theta. So this can be any angle right here, theta. Okay. Well, we know one thing, and this is the fact this is what we're gonna have to work with, is that our force acts perpendicular to this beam right here. So the angle from here to here, perpendicular. We know that too. So here's what we're going to have to do to try and get around this. So if I were to draw a horizontal line right here, well, we know that this angle is still going to be theta. Okay, well, that's pretty obvious. And if we go to this side, so it's the same horizontal line, we know that, of course, the angle between a horizontal line is 180 degrees. And if the first part is theta, the second part is 90 degrees, we know that the angle on the other side is going to be 90 minus theta. And that's what you have to know. And now this is nice because we have an angle that goes from a horizontal axis right onto our force. So what we're going to do in our example above is we go, okay, we see that the angle of the beam goes 4 meters in the x direction and then 3 meters up. So it's going to be the opposite when we look at this force. So I'm going to label this, let's say in pink, just to show you guys exactly what I mean. So I'm going to actually erase some stuff just to make it very, very, very clear. So if I'm going down and then across, so remember, it's going to be 90 degrees minus theta. So if I look at the beam, it spans 4 meters and goes up 3 meters. So my force will be the opposite, where it goes 3 meters across and 4 meters up. And of course, the other side will still be 5 because 3 squared plus 4 squared equals 5. And if you guys want, just to kind of prove this, instead of me just saying the number switch, what you can do is you guys can find the angle right here, theta, using these numbers very easily. And what you'll see is that this angle right here is going to be 90 degrees minus theta. But it's up to you guys. Whatever, and if you guys just want to believe me, that's fine too. Hopefully I don't steer you guys in the wrong direction or anything like that. But no guarantees. So it's just remembering that, because this is what students have a lot of trouble with, is just finding the angle that the force makes with the beam. And the biggest problem that I see students doing is they say that this angle, which is actually 90 degrees minus theta, is they'll just say it's theta. They think, okay, well, it has to be somewhat easy, so they just assume theta. Usually leads to some problems. So if you guys are in doubt, please just try the trig. You guys are very smart at trig. I know you guys can figure this out real quick. All right, moving back on. We can go to our other equilibrium equation, so it doesn't matter which one. So I'm going to go sum of the forces in the x direction is equal to 0. It's just kind of my go-to after the first one. So I have by there, but I have it in the negative x direction. So I'm going to go minus bx, and I'm going to go up, and I look, and I got a force, and it also has an x component, but it's also going in the negative direction. So minus my force, which I already know is going to be 4,000. But remember, that's the total force. I'm only interested in the x component. So I'm going to take its component in the x, which is 3, and divide by the hypotenuse. So I'm going to have 3 over 5. And we all know that this is all equal to 0. So when I solve, I'm going to get bx is equal to, and it's going to be a negative, and what I get is negative 2,400. And this, of course, would be newtons. So remember, when we're dealing with reaction forces, we're guessing the direction. We don't know the direction. We're just taking a guess. And if we look at this case, our guess was wrong because we had negative. So what I'm doing in my final answer is I'm going to say bx is equal to 2,400 newtons. So I'm keeping it positive. But what I'm going to do is I'm going to show the correct direction. So we know that we assumed, oops, sorry, this is wrong, but let me go up here. We assumed that it was going left. It was negative, so therefore the actual direction means it's going, oops, I don't know what that was. The actual direction is going to the right. So a negative just means that your direction is the opposite of what you assume. So if you guys get a negative number, don't worry, completely fine, nothing bad. Oops. I don't know why it's kind of cutting off there. All right, let's try this again, round 2. Perfect. So we got bx, we got ay. If we sum the forces in the y direction, we can solve for by, which is our last unknown. So if we go sum of the forces in y equals 0, well, we know that by is an unknown, and we know that ay was an unknown, and we know it's going up. So instead of ay, I'm just going to add in the 3,333 newtons. And then we know that we had a component of the force F that was going down, so minus 4,000. But we want the component of it. We look up here, well, that'll be 4 over 5. So come down here, we're going to put in 4 over 5 in the bracket. We know this can be equal to 0. So if we solve that, what we get is by is going to be equal to 133 newtons. And we actually find that it's in the downwards direction. So what you do if you solve for by right now, you'll get negative 133. And since we assumed by is going up and it was negative, it just means it's in the opposite direction. So that means that by is actually going downwards. And if we look here, it kind of makes sense, because the best thing to do just to kind of check is just use your intuition. If I have a lot of force coming down on this side of the beam like this, it's going to want to pull the other side of the beam up. So the beam is going to want to move up like this. So the reaction force at B must kind of pull it down so it doesn't rotate over. So that's kind of a good way of checking. And we see that it's very low because the cantilever side so this cantilever, it's not huge. If that went way over, let's say a couple more meters, the reaction force, of course, would increase a lot. And if there wasn't any cantilever there, so if I were to, let's just say, remove everything in pink on this side, and that wasn't there, then the reaction at B would start going in the actual upwards direction, which is what most of you guys expect. But it's a good lesson for you guys, because I know a lot of people assume that the reaction force of a pin always goes upwards. Not always the case, as we see here. By is actually going downwards. So we solve for our 3 reaction forces. The question is done. So just kind of looking back on the question, we looked at an angled beam. What's so special about it? Well, nothing. The only thing you're really going to have to do is just find the angle the force makes with the beam. And we just already determined, not too hard. So thank you guys all so much for listening. I'll see you guys in the next tutorial when we talk about trusses. So we're not going to get into trusses. Trusses are for a later week. Lots of fun. You guys will learn that I love trusses. Lots of calculations. But we're going to just talk about the support reactions of trusses. Because again, like I said, this week is the fundamentals of something huge, which is coming up, and that's everything. So thank you all so much for listening. I'll see you guys in the next video.